Okay, today we're going to do our last topic for this chapter. We're going to look at using trig equations to solve real-world applications. On the title page here, I've got a little small picture of a Ferris wheel. So if you were a person going on the ride, you would get on at the bottom. You can see we're at a height of 1. And as you ride the ride, you go around the Ferris wheel. You get to a height of 7. And then you would come back down to start all over again. So if we were to actually graph that, you could see we start at height of 1 at time 0. We would get to the peak at 7 meters, and in this case at time 5 seconds, 5 minutes, whatever the case is. And then we'd take another 5 minutes to get back down to the starting point, and then it would keep repeating. So you could see that, and we assume that everything's constant, so at time 0 we're at the bottom, when we're at a height of 4, you can see that would occur halfway, so at 2.5 minutes. And we'd get to the height at 7 at 5 minutes, and back down. If we're at the 3/4 way, we'd be back at a height of 4 again at 7.5 minutes, and so on. So the idea is we can often use trig graphs and trig equations to solve or to simplify, to analyze a real-world application. So types of examples we could do is the height of tides. So in a normal situation, our tide heights go up to high tide, they go down to low tide, and they just keep repeating every 28 days or so. Weather temperatures. So we know that if we did the average temperature of Leduc in January, it would be minus whatever, minus 10, minus 15, and it would get warmer and warmer until we got to summer, and then at summer it would get cooler and cooler back to winter, and that cycle just keeps repeating year after year. So over the course of a 12-month period, we would get one complete revolution of weather. Height above ground on a Ferris wheel, so that was the last picture we just looked at. That would work. The swing of a pendulum, so if you're on a swing, we could graph we could do height. So we do height of the pendulum over time, things like that. So similar to a Ferris wheel, we could draw all of these things. So any kind of situation that repeats over and over again, we can often graph it and get a sine or cosine type equation to analyze it. So the question then is, how do we do these kind of questions? Well, really just like anything else, we want to be able to sketch the graph, and from the graph determine the A, B, C, and D values. Often in this case, if you have trouble, sometimes the amplitude, remember, we could just do max minus min divided by 2. So sometimes that works good in terms of if you get data in charts or something like that. And then the midline is the average, so the max plus min divided by 2. So both of those you can get pretty easily from the data. The B is usually quite often given from the data, not directly, but if we knew if it was a weather temperatures, our period would be 12 months. So we'd go 2 pi divided by 12. If we're talking about a Ferris wheel making one revolution in 1 minute, we'd have 2 pi divided by 1 minute. So the B usually you can get from the equation or the data given. The phase shift, usually you have to draw the graph or sketch the graph to figure out what the C value would be from the graph only. So let's do an example. So this one, it shows average temperatures over the course of a year in Whitehorse, Yukon. So you can see in January it starts at negative 18.4, heats up until we get to July, and then it gets cold again on the way down to December. So if we were to graph this, typically what we would do in this case is we would put temperatures on one scale. Oops, let me erase that. So we would do temperatures on one scale, and we would do the time or the months on the other scale. Okay? So our temperature in Celsius, we can see we go from negative 18, so let's put about negative 20, and we go up to a maximum of about 14. So we can go from 20 to 20 would be a good scale. And we would do our months from month 1 up to month 12. Okay, so if we plotted this, we'd see we'd start at negative 18, so at month 1 would be at negative 18, something like that. The question is, do we call January month 1 or we call it month 0? I guess it really doesn't matter too much. Let's do it as month 0. That might make it a little bit easier. So January would be at negative 18. February would then be at negative 13. March, negative 7. April, it's almost at 0. May, we're up to 6. June, we're at 11. July, we're at 14. And then we start dropping again. We're back to 12. About 7, almost at 0. -9. And by the time we get to December, we're down to about -15. So if we actually were to draw this graph, you could see we end up getting a pretty good sine or cosine type graph. So the question is, with this kind of graph then, is how do we actually figure out our equation? So let's go through our ABCD. So first off, let's do our amplitude. So we can see that our maximum temperature is 14 and our minimum is -18.4. So our amplitude is max minus min divided by 2. Okay, so let's do that first. Actually, let's just go back to the formula for a sec. Yeah, amplitude is max minus min, midline is max plus min. Okay, so we want to go -18.4, subtract that from 14. Okay, so let's do that. So we get an amplitude of 16.2, and let's do our D while we're at it. So it'll be max minus our max plus min. So we'd have -18.4 plus 14, which give us -4.4, divided by 2 would give us -2.2. So based on our graph, let's just see if that's right so far. So we'd have a D, a downshift of -2, so that'd be somewhere about there. So that looks like pretty close to the middle, and we've got a height of 16 top and bottom, which looks good. So our amplitude and our D is good. So now the next one is our B. Our B value, remember, is 2 pi, do this in radians, divided by period. Our period for a year is 12 months, so we go 2 pi divided by 12, which would be pi by 6. And our last one is our C value. So the only trick is, how do we want to do this? Do we want to use a sine graph, cosine graph, and so on? So let's do a sine graph, and you can see we would have, for our sine graph, we want this value to be at the origin, so you can see we're at about 3 months shifted. So April is at our 0 line. We want to go 3 months over, so we would just write that as, in terms of months, we would say 3. So our equation then should be y equals 16.2 sine 3, or sorry, pi by 6 times x, we're going to the right, so that'd be -3, and our d is -2.2. So that would be a pretty good equation to model our temperatures for this situation. Okay, let's do a different one. So here we got a Ferris wheel. It says our Ferris wheel is a diameter of 20 and a height of 22. So let's sketch this. So we've got our Ferris wheel. If it's got a diameter of 20, so that's our distance across, but above ground it's got a height of 22, so that means we've got 2 meters space between the ground and the bottom of the Ferris wheel. So in this case, riders are going to get on the bottom, and they're going to make one complete revolution in 1 minute. Okay, so let's figure out our ABCDs again. So in this case, our amplitude is going to be the radius of our circle, right? We're going to, if you think about this, let's kind of sketch this out a little bit. We're going to start at a height of 2. That's where we're going to get on the ride, is at 2. We're going to go up to 22. That'll be our maximum height above ground. And we're just going to repeat. So we're going to go up to 22 and back down to 2 and so on. So in this case, if we think of it in terms of the graph, our midline should be halfway between 2 and 22, which would be at 11. So in this case, we would have a D of, oops, sorry, I messed up. Halfway would be 12. Right, so we have a diameter of 20, that means we have a radius of 10. So we're 12 meters above ground, so that should be our D. And our amplitude would be 10. We're going to go up 10 and down 10 from that midline. So that's pretty easy. Our B value is 2 pi divided by our period, and our period in this case is 1 minute. So we just have 2 pi divided by pi, as long as our values are in minutes, which it should be. And our height would be in meters. And that's it. So all we got to do now is figure out our C value. So we've got our y equals 10 sine 2 pi. We have time, or x, whatever we want to call it, plus or minus something, plus 12 for our d. So the only real trick with these is usually finding the C value. So what we want to do is use the graph to help us figure this out. So you can see that we were at 2 meters to start with at the bottom at time 0. At 22 meters we're at the peak. Then we went back to the bottom. So the one complete cycle took 1 minute. So we'll do that as 1 minute. So that means halfway would be half a minute, or 30 seconds. So remember, with a sine graph, we want it to go starting right there. So that would be basically, if we're starting at the bottom, top was halfway. So what we're looking for is what time did it take to get to that far left position, which would be halfway again, so at 0.25. And that's it. So we've got 0.25 minutes, and we're going to the right, so that should be negative 0.25. or a quarter if we wanted to do it as a fraction. And that's it. So that's it for trig applications. Usually the same kind of issues that we had before, just figure out your A, B, C, D, and you're going to use a combination of the data that they give you plus a rough sketch to help you figure out the C value especially, and that's all.